Welcome to today's webinar. Today we show you how to analyze an aluminum scaffold in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Global Software. For instance, technical content of the website, German and English webinars, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Sonja von Bloor will be the presenter of this webinar. She is responsible for the development of the add-on aluminum design and also for the standalone program R section. Yeah, and she works also in the customer support team. Okay, then I say something how you can ask questions, at least for the attendees who participate the first time. First, I switch off my webcam that you can see the full screen. Yeah, if you have a question, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@global.com. Okay, that's at the moment all from my side. I hand over to Sonja. Sonja, you can start.
Thank you, Andreas, for the introductory words. I would also like to welcome you to today's webinar. The topic of this webinar is the modeling and design of aluminum scaffolding. First, I will demonstrate how to model the scaffolding in Rfem, focusing particularly on the realistic representation of scaffold connections and supports. In the next step, the loads, imperfections, and the required load combinations are created. The load combinations are based on user-defined action combinations. To keep the number of combinations as low as possible, I will explain how to define dependencies between load cases so that certain load cases are not considered together. Finally, I will introduce the design using the aluminum design add-on and explain the most important steps and settings. Let's start with the first step, modeling the aluminum scaffolding. Rfem offers various modeling aids, such as building grids and guidelines that facilitate input, for example, by snapping points at the intersection of these guide objects. Building grids and guidelines can be found in the navigated data under guide objects. Here, for example, you can easily create a new building grid by specifying the grid line coordinates here. CAD files can also be imported, either for the direct creation of members or as a background layer to support modeling. Import from Excel is also possible. You can find the import functions on the File menu. Numerous import formats are available here. Recurring components can be saved as blocks and reused as often as required. The geometry and loads of these blocks can be flexibly adjusted using parameters. The blocks are managed in the Block Manager. The Block Manager already contains a variety of blocks that you can use for modeling. Your custom blocks are also managed here. Alternatively, it's possible to model the objects individually and combine them into the overall structure using functions such as copying or mirroring. Today, I'll show you the latter approach and start by defining the materials and cross-sections. For the scaffolding, I'm using an material. I import this material from the material library. Here I search for an EMHW 6082 material and I import this material in my list. The base jacks are made of steel. So for this, I create a new material and I import this also from the material library. It's an S235. Then I create another material for the platform units. These platform units are made of wood, and it's a C24. Then I can define the cross sections. The standards, ledgers, and guardrails have a tabular cross section. So I create this first. The material aluminum is preset here in this case, so I go directly to the section library, and here I search for 48.3 for tubular cross section. The bracing in vertical plane uses the same material, but with the slightly thinner cross section. So for this bracing, I create a new cross section, and I import this cross section also from the library, 48.3 and 3.2. The base jack is made of the tubular cross section and made of a steel material. For this, I create a new cross section. I choose here the material S235, and then I define the parameters of this hollow section by defining the geometry. It's a 38 millimeter diameter and a thickness of 4 millimeter, and it's a cold formed cross section. The platform units have a rectangular cross section made of wood, so for this I create also a cross section. I choose here the C24, and then I define the parameters of this rectangle, and it's 320 millimeter and 40 millimeter height. Then I can define the structure. The base jack is modeled as a beam member. I will do this now. So I open here the member dialog. Then I assign the command base jack so that I can make targeted object selections later. Then I go to the tab section and select here the steel section. And then I can model my member. I use here the input mode, length and direction. The angle in the work plane is 0 degree. The member length is 0.4 meters. I have to reverse the orientation, and then I position this member at the coordinate origin. Then I define the supports here on this node. For this, I activate the support option. Then I can create my support. In the vertical direction, the standard can only take compression, but not tension. This is represented by a nonlinearity failure all if negative PZ. The horizontal forces are transferred to the subsoil via friction. The friction depends on the support force in the vertical direction. For the UX and UY direction, I assign therefore the nonlinearity friction pz. Friction coefficients are listed in Annex B of EN 12812. The base plate rests on a wooden slab. The standard specifies friction coefficients between steel and wood of a minimum of 0.5 and a maximum of 1.2. For the calculation, I choose an average friction value of 0.85 for the UX and UY. According to EN 12811 Part 1 and EN 1065, a bilinear spring with a moment rotation characteristic can be applied to the support base jacks with a rigidly connected end plates. Rfem provides the appropriate solution for this using the nonlinearity scaffolding hinge. The required torsional spring properties and the degrees of freedom Vx and Vy can be considered in accordance with the standards. I only have to define the parameters of the scaffolding hinge. I define a rotation angle Vy equal 1 degree. Since the unit is in milliradians, you have the option to switch to a different unit or manually convert the angle. I perform the conversion. So here I calculate P divided by 180 multiplied by 1000. Then I define the stiffness. This should be 30 kilonewton meter per rad. The definition type should be relative. Here I use the default settings for the eccentricity factors and I import the outer diameter from my base jack. Then I define an end plate thickness of 10 millimeter. Let's look at the diagram here. The support remains moment-free up to the defined rotation angle V0. After that, the rotation no longer changes up to a moment of ME0, and this ME0 moment is calculated by the slip eccentricity factor multiplied by the total thickness multiplied by PZ. Between this moment and the maximum moment, the support reacts with a torsional spring stiffness. The maximum moment is calculated by the maximum eccentricity factor multiplied by the total thickness multiplied by PZ. After reaching this maximum moment, a yield process is initiated. Then I create the standard. The standard is modeled as a beam. Here I use the command standard and I use here this cross-section, this aluminum cross-section, and then I can start to create this standard. For this I use the input mode length and direction angle in the work plane is 0 degrees, member length should be 2 meters. I reverse here also the orientation, and then I create this member. EN 12811 Part 1 allows the joints between tubular members to be treated as rigid, provided certain design conditions are met. These include, for example, sufficient overlap length or that a certain limit for the play in the joint is not exceeded. Since these specifications are met by the scaffolding system used, I do not need to define any hinges for the connections. Rfem also offers special scaffold hinges that can be used to accurately simulate the mechanical effect of a plugged tubular joint with an inner tube stub between two members. I will show you this also. Here you have to define the option hinges, and then you have to create a new hinge. And here you find the nonlinearity scaffolding, and then it's possible to define the scaffolding diagram for the inner tube and for the outer tube. I then copy the base jack and the standard. For this purpose, I select them first, and then I open the Move Copy dialog. I want to create a copy. Displacement vector is in X direction 2.57. I can now create the ledger between the two standards. Command is ledger. Section is here this tubular aluminum cross section. The ledger is connected to the column via a coupler. Therefore, I activate this option hinges and create a new member hinge. The joint stiffnesses specified in the approval are described there as a function. This function can be realistically represented in Rfem using the diagram nonlinearity. I import the diagram from a prepared Excel file. The joint is only effective up to the maximum moment value, so I select yielding. The torsional spring stiffness Pz is 5.1 kN per rad. I assign now this member hinge to the member start and member end. The approval also defines connection eccentricities. I want to consider them too, so I activate here this option eccentricities, and I define a new member eccentricity. Eccentricity type is absolute. I refer the eccentricity to the local coordinate system. It's 25 millimeters in X direction. I create also an eccentricity for the member end. Absolute here in negative X direction. I can now create this member. I then copy the entire structure. Displacement vector is here in Y direction 0.73. And I can now create the transoms. For this, I create a new member. Command is transom. Section is here the same section as for the ledges. The hinge conditions are also the same. and also the eccentricities. I then create here these transoms. I then create the longitudinal diagonals as a beam member, longitudinal diagonal. The longitudinal diagonals have a thinner cross-section, so therefore I choose here this cross-section number 2. The approval specifies that the load displacement behavior of the vertical diagonal must be considered with a translational spring. This translational spring is different for tension and compression. Therefore, I create here a new member hinge and I use the nonlinearity diagram for this. To define different diagrams for compression and tension, I deactivate the symmetric checkbox. I then define the parameters. It's minus 10.2, minus 16.6, 0, 0, 12.9, and 18. I define the rotational spring stiffness about the y-axis as hinged. Here I deactivate this hinge and then I assign this hinge to the member start and member end. The approval also defines eccentricities for the vertical diagonals. At the start of the member, I create here a new member eccentricity. Eccentricity type is absolute. I refer this to the global axis system. And here it's minus 77 in X direction and in Y direction it's 50 millimeter. And for the member end, I do here the same, 77 and 50 millimeter. I can now create the longitudinal diagonal. I then create the transverse diagonal. For this, I create a new member. Section is here the same section as for the longitudinal diagonal. Also here the hinges are the same, but I have to define new eccentricities for this. So I create a new eccentricity. It's minus 50, 77 for the member start and minus 50 and minus 77 for the member end. I can now create here my bracing. For the static analysis, the axial stiffness of the vertical diagonals should be assumed to be nearly infinite. This is because the spring values defined in the approval replace both the stiffness of the diagonal members themselves and that of their connections. In Rfem, this can be implemented by structure modification, in which the axial stiffness is increased by a factor. you find the structure modifications in Navigator Data, structure modification. Here I create a new structure modification. I want to modify the stiffness of the members. Here I create a new stiffness modification. Modification type is multiplier factors of partial stiffnesses. And here I increase the axial stiffness by a factor. And then I have to assign this structure modification to my bracings. I then copy the scaffolding 2 meters in negative Z direction. For this, I select here the objects. Then I choose here the move copy function. And here I change the displacement vector. And I copy then these members. To model the guardrails, I define nodes on the standard using the nodes on member options. For this, I select the corresponding members and I edit them. Then I activate this option, nodes on members. I use here the definition type string and I change here to the absolute distances. And then I can create the node distances. It's 0.5 and 1. The nodes were created here, as you can see. And then I can create the guardrails. For this, I create a new member. Command is guardrail. Section is here section number 1. Hinges are the same as for the ledgers. And also the eccentricities are the same like for the ledgers. Then I can create my guardrails. To model the platform units, I define nodes on the transoms using the nodes on members like for the standards. For this, I select the members first. Then I activate the option nodes on member. I use here also the definition type string, absolute definition, and here I define a distance of 0.18 and 0.5 meter. Then I can create the platform units. Here I change the section to the rectangular cross section. I define here a new hinge type. It's hinged in a free Y for the member start and for the member end. And I don't need an eccentricity here. So I can now create the two platform units. The scaffold is connected to the facade at 4 meter and 8 meter using anchors according to EN 12-811 Part 1. The connection between the anchors and the facade must be modeled so that the anchors can rotate freely around all axes in the plane of the facade and no vertical forces are transmitted. For simplicity, the anchors are modeled directly on the scaffold using supports. So I select here the nodes where I want to create my supports, and then I create a new support type, and I define here the corresponding parameters. The entire scaffold can now be created by copying mirroring. I've already prepared this. For this, I open here the prepared file. In the file, I've also already created object selections for the scaffolding components. You find the object selections in navigated data under guide objects, object selections, and these were generated using the comments stored in the member. So for the standard, comment equals standard. For the longitudinal diagonal, comment equals longitudinal diagonal, and so on. The object selections are also available as visibilities in the navigator views. So if you activate here the standards, you can see the standards, guardrails, and so on. In the next step, I define the actions. There are 3 types of loads that must be considered according to EN 12-811 Part 1. These are permanent loads, such as the dead loads of the scaffold, including all associated components, such as protective roofs, variable loads, such as live loads, wind loads, and possibly snow and ice loads, and accidental loads. The only accidental load specified in the standard is the downward load on the side protection. EN 12-811 Part 1 recommends considering wind loads parallel and perpendicular to the facade separately in the calculation. Furthermore, 2 combinations must be considered when designing a scaffold: the service condition and the out-of-service condition. The service condition corresponds with the self-weight of the scaffolding, a working load on the scaffolding, and a working wind load. The out-of-service condition corresponds with the self-weight, a percentage of the working load, and the maximum wind load. I now define the load cases in which I can generate these actions. The load case self-weight is already created here. Here the active self-weight checkbox is already activated so that self-weight will be automatically calculated. I define another load case for my service load and service condition. Action category is imposed loads. I copy this load case for the out of service condition. Then I need to create the load cases for the working wind loads parallel and perpendicular to the facade. Action category is here wind. Working wind load X parallel to facade. Working wind load Y perpendicular to facade. And then the maximum wind load parallel and perpendicular to the facade. I don't consider the accidental load. Now I can define the loads. The dead weight is calculated automatically, as I said before. But since I've excluded the toe board from the model, I apply the dead weight of the toe board to the ledges and the transoms. For this, I open the self-weight load case, and here I use my visibilities for the ledges and the transoms. And then I create here a new member load with a load magnitude of 0.0 2020 kilonewton per meter in Z direction. And I apply this load to the front members and here also to the side members. This load case is now complete. Then I can define my service loads. For this, I change to the load case number 2. The service load to be applied during service conditions is determined by the load class. The scaffold must be designed for load class 3 according to table 3 of EN 12811 part 1. This corresponds to a uniformly distributed load of 2 kilonewton per square meter. The service load is applied to the scaffold level that leads to the most critical loading. Typically, this is the top level. According to the standard, 50% of the load must also be applied to the scaffold level immediately above or below the critical level, which corresponds to 1 kilonewton per square meter. For the service load, I use the load wizard, member loads from area load. For this, I go to the navigator data, and here you find the load wizard member loads from area load. This tool allows surface loads to be easily distributed onto the relevant members in the model. The wizard calculates the load shares automatically, so I don't need to do it manually. The load magnitude is 2 kilonewton per square meter acting in global Z direction. I define the surface load plane by selecting the corner nodes. Since the load should only act on the platform units, I remove all other members from the load application. To do this, I pick these members in the graphic. A surface load of 1 kN per square meter is applied to the scaffold level below. For this, I create a new load wizard. I define here a load magnitude of 1 kN per square meter. Then I pick here the corresponding nodes. And I also remove the influence on the ledges and the transoms. Then I apply this load. This load can be shown also as service load. For this, I deactivate here the option display separately. For the out-of-service condition, a percentage of the uniformly distributed service load must be applied to the relevant scaffold level. The percentage depends on the load class and amounts to 25% for load class 3. This corresponds to 0.5 kN per square meter on the top scaffold level. To do this, I copy the surface load from the service condition on the top level and change the load magnitude. To do this, I switch here to the load case number 3. Then I open here the load wizard. Then I copy the load, change here the load magnitude to 0.5, and then I change here also the load case where this load should be generated, and I click then on OK. You can also use the load wizard to generate wind loads because the input is very similar to that for the service load. I've gone ahead and prepared it already. So I open the prepared file. You can see here the working wind loads parallel to the facade, perpendicular to the facade, and the maximum wind loads parallel and perpendicular to the facade are already defined. So on the next step, we can focus on the design. In this webinar, I will concentrate on the ultimate limit state design of the standard. According to Eurocode 9, a second-order analysis considering the relevant imperfection is permitted. In this case, only cross-section checks are required, since stability effects are already captured by the analysis. The connections between the standards have been modeled as rigid joints. However, to account for the rotational play resulting from the slip in the plug connection, EN 12811 Part 1 requires the consideration of frame imperfections by angular deviations at the joints between vertical components. In addition, the maximum permissible vertical deviation of the base jack must be taken into account in the calculation. First, I create imperfection cases in X and Y directions in which the relevant imperfections are defined. To do this, I go to the Navigator data and create here a new imperfection case. And this is the imperfection case for the imperfection in X, and another one for the imperfection in Y. Since I only want to perform the design checks for the standards with the scope of this webinar, I define the imperfections only for the standards. In the imperfection load case X, I define the initial sway with a ratio of 1 divided by 30 for the base check, and then 1 divided by 100 alternately in positive Z and negative Z direction for the standards. For this, I define a new member imperfection. Here I choose the imperfection type initial sway, the definition type relative. Initial sway should be 1 divided by 30. Imperfection direction is Z. And then I choose here the base check. And then I click here on apply next. Then I define an initial sway for the standard. And I choose here these members, click on apply and next. Then I change the imperfection direction and choose then the other standards. Apply and next. Next, I define the initial bow with E0 divided by L equal 1 divided by 150, alternately for the standards. So I choose here initial bow 150. Then I choose the corresponding members. These are these members. Click on apply and next. Then I change the imperfection direction. And choose here the other standards. It's now possible to copy imperfection to other standards. Let me open my file where this process has already been completed. So I open here this file where I've already defined the imperfection in X and in Y direction. I can now proceed to set up the necessary parameters for load combinations for the ultimate limit state according to EN 12-811 Part 1. Partial safety factors of 1.5 must be applied to all permanent and variable actions. The load combination can be represented in Rfem using a user-defined load combination. For this purpose, I open here the load cases and combinations. Then I go to the design situations and open the combination wizard. And then I activate here this option, user-defined action combinations, which allows me to define the action combinations user-defined. In the next step, I will do this. So I create here a new user-defined action combination, and there I assign all these actions, but here with a partial safety factor of 1.5. Then I go to the actions to ensure that the service loads are not combined with each other. I set the action type to alternatively for this action category. For the wind load, this setting is already applied by default. The service loads for the service condition should not be combined with the maximum wind loads. Furthermore, the service loads for the out of service condition should not be combined with the service wind loads. This can be accounted for in Rfem by using exclusive load cases. Therefore, I activate the checkbox Consider Inclusive Exclusive Load Cases, and then I create a new relationship between load cases. Then in the Exclusive Load Case tab, I specify that the load case 2, that means the service load in service condition, should not combine with the load cases 6 and 7. This means the maximum wind loads, and that the load case number 3, that means the service load out for the out of service condition, should never combine with load cases 4 and 5, so with the working wind load cases. In the combination wizard, I activate also the structure modifications so that the structure modifications are considered in the calculation. Furthermore, the imperfection cases are to be included in the load combinations. Here, the corresponding checkbox is already activated. However, the imperfections in X should only be combined with the wind loads in X direction, and the imperfections in Y only with the wind loads in the Y direction. For this purpose, I open the Edit Imperfection Case dialog. Then I select all my imperfection cases and I deactivate this checkbox assign to all load combination without assigned imperfection cases. Then for the imperfection case X, I assign the loads in X direction, the wind loads in X direction, and for the imperfection in Y, I assign the wind loads in Y direction. Now the load combinations can be generated. The scaffold as well as the loads are now fully defined. So in the next step, I can proceed with the settings for the aluminum design. To do this, I first activate the corresponding add-on. Here, I do this in the base data. And here I activate this add-on aluminum design. Then I choose here the corresponding standard and national annex. Then I switch to the table of the aluminum designs. Here in the objects to design, I select all the standards. To do this, I deactivate this checkbox here, and then I select the standards by the help of the visibility of the standards. Additionally, I deactivate the stability design in the ultimate limit state configuration. For this, I open the ultimate limit state configuration. This is because the calculation is performed according to the second order theory and imperfections have already been considered. Therefore, only the cross-section checks are required as stability effects are already captured by the calculation itself. I can now run the calculation. The utilization ratio for all standards is below 1, which means that the cross-section and stability checks for the standards are fulfilled. That brings me to the end of the webinar. I now hand the floor back to Andreas.
Thank you, Sonja, for your presentation. At the end, I have a hint for you. You can book our online courses, for example, the Rfem 6 Masterclass course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design, Eurocode 3 for the steel design, and the Eurocode 5 course for the timber design with Rfem 6, where are also course packages available. For more information, just scan the QR codes in the middle, or you can click the buttons on the bottom of the page for the single courses or for the packages. You can download the slides from the same website where you can find the recording. In the next days, you will get an email with a link to that page, and you will also find the model that Sonja showed today, and you can download it. Another hint, you can get the single courses, that means the Rfem 6 course or the Eurocode 2, 3 or 5 course for free when you send us a customer project and we publish it. Just write me an email and I will answer you what I need for materials. It's not much work for you, I promise. Okay, that's also all from my side. I thank you for your attention. Thanks to Sonja for her presentation. I wish all a nice rest of the day. Bye-bye.